Okay, right, question 15, vectors. We're going to jump straight in and try and have a go at this from the start. So all the information that was in the question is now on the screen, apart from the diagram. And I don't know if you're somebody who isn't getting these right very often, why you wouldn't have a diagram is, it totally baffles me. I cannot work with these questions purely just using the vectors. I need a picture. It is sort of a spatial geometry question. So let's get started on trying to label up what we know. So the position vector, and because it's got the origin here, this is the actual coordinates of A. O to A gives you the actual coordinates of point A. So we can write those in. So the position vector for A is this. Alright, so that's fine. We've got another position vector here, so those are the actual coordinates for B. So that's 3, -1, and our constant P, which is a value we've got to find at some point. And we also know some other relationships here. So we've got C and D. We're told in the second part it's trapezium, that's why I've drawn it in this way. We are told B to C, so this kind of connection here, B to C, this vector B to C, I'll label it for us. So put the arrow in the middle. The column vector for this, now this is a directional vector because it's not from the origin, it's just from B to C. So this is 0, 6, -7. Okay, and that is how you describe this journey here, this length and direction here. A to D, so this one here, A to D, label this on, is going to be 2, 5, -4. That's all the information we have, and we've got to firstly find the position of vector D. So, to get to D, the origin, let's say, I don't know, the origin could be anywhere, over here. To get to D from the origin, we want the position of D. Excuse the straight line here, that is terrible. That's the journey that we're looking for, but we don't know where D is. So we've got to go on another route. We know O to A. O to A is this column vector here, so that's how you get to A. And then if you add on A to D, this one here, you will get this journey because of this triangle law that vectors have. So if it makes a triangle, then this plus this is equal to this journey here. So let's do that somewhere. We are doing OA, vector OA, plus A to D. That is going to give us O to D. Alright, so let's put in the column vectors and do the addition part here. If you understand what you're doing, then the maths is not too difficult. It's quite just adding numbers. -3 to 7 plus the direction vector AD, which is 2, 5, -4. This will give us this we've got to be careful. Get a calculator out, I would, if you're allowed one. -3 plus 2 is going to be -1. I'm trying to do this in my head, be very careful. 2 plus 5 is 7. And 7 plus -4 is going to be 3. So this is my O to D, and that is actually the coordinates now. That's the position vector of D. So I know where D is exactly. Okay. So that gives you the first mark for O to D. Now we've got to work out the value of P. And we're going to need to exploit a relationship here from GCSE vectors about parallel vectors, because we need a relationship. We know that A and B on our trapezium, so this A to B line here, is going to be some multiple of this line here, D to C. Alright, so if I could work out D to C and A to B, there'd be a relationship here, and I know that A to B is going to have P in it. I can see because P is part of the B coordinate here. So I need both of these. I don't know what C is yet, and that could be a problem. So I probably should work out the position vector for C. And I'm going to use the same technique. I'm going to go O to B, which is already given there, and then B to C. So I'll do this here somewhere. What did I say? O to B plus B to C. That's going to give me the position vector of C. So we call that OC. Very popular TV show back in the early 2000s, the late 90s, the OC. Let's have a look at this. So O to B is 3 minus 1 P. And then we've got a 0, 6, and minus 7. So I'm going to get 3 minus 1 plus 6 is 5, and P plus minus 7 is just P minus 7. So that's C. And I've already put in the bracket there, so let's the column vector, I should say, let's label that. So P minus 7. So we have all the coordinates of all the four corners. Let's start to work out these journeys that we're going to exploit. So let's do A to B, and if you want to work out A to B, you should know the standard result for A to B in vectors is B minus A. So column B minus column A will give me the result for this. Will give me this answer here. I might actually just write it in there once we've done it. So let's put in 3, this is for B, minus 1 and P. A is minus 3, 2, 7. Put the answer straight in here now. 3 minus minus 3 is 6. Minus 1 minus 2 is minus 3. And P minus 7 is P minus 7. So that is A to B. That's the journey A to B there. Okay, so that's our answer there. Let's do the same for this down here. So if we want to go from D to C, we're going to have to use, come back C, where we go? We're going to use C minus D. So I'll write that underneath, C minus D. Put the answer in here. C is 3, 5, and then that's going to be awkward, P minus 7. Minus D minus 1, 7, and 3. Okay? 3 minus minus 1 is 4. And 5 minus 7 is minus 2. And P minus 7 minus 3 is going to be P minus 10. So, we have these two column vectors here, and they are parallel. So there is some links. One is a multiple of the other. You can see 6 and 4, what is the relationship? It needs to be the same relationship as minus 3 to minus 2. And it needs to be the same relationship with P minus 7 and P minus 10. Now, if I know that there is a relationship between these x parts, so the top number 6 and 4, one is a multiple of the other. It's like scale factors from GCSE. You know when you did scale factors from two similar triangles, you would always do the big number divided by the small number. So I know that this scale factor is 6 over 4, which is also going to be equivalent to the one in this section here, minus 3 minus 2, minus 3 over minus 2. You can choose any of these. Just check them both though. What does that give me? 6 divided by 4 is 1.5, which should equal minus 3 divided by minus 2, which is also 1.5. So the scale factor is 1.5 times bigger than this. The diagram is misleading. I've obviously just chosen a random Google image trapezium. So it should be the other way around for the lengths. Alright, so apologies for that. But now we know that this P minus 7, this is what we wanted. The P minus 7 from A to B is equal to 1.5 times, it's 1.5 times bigger than the P minus 10. That's the relationship, okay? You know, if you don't understand where it's come from, if I set it up with a different one, like I'll use the 6 and the 4 to set up the same relationship underneath. Well, then I'll do it over here. Just to give you an idea, 6 equals 1.5 times 4, right? See what I've done? The 6, 1.5 times 4, they are equal. Yes, that is true. So this must be true here. So P minus 7 is equivalent to 1.5 P. What is 1.5 times 10? Well, that's a nice decimal for us to work with, 15. Rearrange this. We're going to subtract 1p from both sides. So I'm going to get 0.5p that side. Let's add 15 to this side. So it's minus 7 add 15. It's going to give me 8. So 8 is equal to 0.5p times both sides by 2, and you'll get 16 is equal to p. That's the value that we were looking for, and that it should be the answer. I hope that's helpful. See you in the next video.